Let's look at a little bit more complicated example of this. All right, so there's my overall equation that I want to balance. Step 1, I start with my oxidation numbers and I assign my oxidation numbers. Step 2 then, want to identify what's being oxidized. Well, what's going to a more positive value there? Well, the bromine in my HBr is going from a -1 to a 0 in the Br2, so the bromine is being oxidized. Now in this example, I'm going to hold on to whatever's attached to that Br- instead of just writing Br-. Okay, so I'm going to hold on to that HBr as one entity. Let's balance this half reaction here. First step, I need to balance everything but the hydrogens and oxygens. So I have 1 bromine on the reactant side, 2 bromines on the product side. So I need to balance those bromines, put a 2 out in front. Next, I need to balance oxygens by adding water. Well, I have no oxygens to balance. Then I need to balance any hydrogens that I have with H pluses. So I have 2 hydrogens on the reactant side, no hydrogens on the product side. So I need to add 2 hydrogens, but in this case I'm going to add them as H pluses. Okay, those H pluses is what's making it be acidic. Now that I've got the H pluses balanced, now I need to balance the charge. Well, my overall charge on the reactant side is 0, my overall charge on the product side is +2, so I need to add 2 electrons. Next, let's look at what's being reduced. Well, the chlorine is going from a +5 to a -1. So the chlorine is being reduced. Once again, I can't separate them out. I'm just going to leave it as KClO3 and KCl. So let's balance this half reaction. I've got 1 potassium on both sides, 1 chlorine on both sides. It's balanced. Remember, I balance everything but the oxygens and hydrogens. Once all those other elements are balanced, now I can look at the oxygens. So I have 3 oxygens on the reactant side, 0 on the product side. I'd need 3 waters. Remember, I add waters to balance out oxygens. So now my oxygens are balanced, but you notice my hydrogens are no longer balanced. So I need to balance my hydrogens by adding H pluses. So how many H pluses do I need to add? Well, I need to add 6 on my reactant side. Now I balance my charge. We've got a +6 on my reactant side, 0 on my product side. How do I get those equal? I add 6 electrons to my reactant side. Okay, so these half reactions are both now balanced. Now before I can write an overall equation though, I need to make sure that the number of electrons are equal in both. So in my oxidation half reaction I produce 2 electrons, but in my reduction half reaction I'm using 6 electrons. Those aren't equal. Okay? Remember, these are half reactions of the overall reaction, so whatever electrons are produced in the oxidation process have to be used in the reduction process. And if they're not equal, we've got to adjust that. So how am I going to get these equal? Well, I can't just add 4 more electrons because that's going to change the overall charge. What I have to do is I have to multiply my oxidation half reaction by 3. Basically, that reaction occurs 3 times to produce 6 electrons so that the reduction half reaction can occur once. So when I put that 3 outside, that means I have to multiply everything by that 3, and I end up with the 6 HBRs, 3 Br2s, 6 H pluses, and 6 electrons. Now my number of electrons are equal to each other. Now I can start writing my overall balanced equation. So the best way to do this is from both half reactions, everything that's on the reactant side, write down, draw your arrow, then put down everything that's on the product side in both half reactions. Okay, so I have 6 HBRs, those are coming from my oxidation half reaction, plus 6 electrons plus 6 H plus KClO3, that's coming from my reduction half reaction. Those are all the reactants from both equations. Then I wrote down all the products from both equations. Next, what I want to do is I want to cancel things out that are similar on both sides of the equations and keep track of the numbers too. So I have 6 HBRs on the reactant side, no HBRs on the product side, so I leave that. I have 6 electrons on the reactant side, 6 electrons on the product side, those can cancel. I have 6 H pluses on the reactant side, 6 H pluses on the product side, those can cancel. I have a KClO3 on the reactant side, no KCl3 on the product side, so those won't cancel. So cancel things out that are the same on both sides, and we end up with this overall balanced equation. Now let's identify the oxidizing agent. Well, the oxidizing agent in this case is the KClO3, because it's what's being reduced, and the reducing agent is the HBr, because it's what's being oxidized. All right, let's look at another example, because it's good to get this practice down. This one will be slightly different from these as well. Okay, so let's look at this equation. We're going to balance it under acidic conditions. So I need to first assign oxidation numbers. Then I need to decide what's being oxidized. I'm going from a -1 to a 0, so the iodine's being oxidized. Need to balance the number of atoms. I then need to balance oxygens and hydrogens. There's none of those in there. So now I need to balance the charge. Do that by adding 2 electrons. All right, what's being reduced? Well, the nitrogen's being reduced. So NO2 minus 1 to NO, I'm going from a +3 nitrogen to a +2 nitrogen. So balance everything but oxygens and hydrogens first. The nitrogens are balanced. Now I need to balance the oxygens. I need one more oxygen, and remember I balance oxygens by adding water. And then I would balance the hydrogens by adding H pluses. Okay, so next I need to balance my charge. I have a +2 plus a -1, that's a +1 on the reactant side, 0 on the product side, so I need to add 1 electron. Next, I need to make sure that the number of electrons are equal in both half reactions. So I have 2 electrons in the oxidation process, 1 in the reduced, so I need to multiply my reduction process by 2. So when I multiply by 2, I get 2 electrons plus 4 H pluses plus 2 NO2 minuses, and then 2 NOs and 2 waters. Now I have equal number of electrons. So write out all the reactants on one side, all the products on the other, and then I need to cancel out things that are similar on both sides of the equation. And that would be my overall net balanced equation. Now I can see a little bit more about how balancing a redox reaction is different than balancing reactions that we talked about previously. Okay, there was no H pluses in the above equation, there's no water in the above equation, but those are necessary in order for this reaction to occur. Now let's look at the last few steps we talked about where we want to balance under basic conditions. So let's say I want to take this reaction and balance it under basic conditions. Remember, whenever I want to balance a redox reaction under basic conditions, the first thing I need to do is balance it under acidic conditions. So go through all of those steps for under acidic conditions. So I ended up with this equation under acidic conditions. Then what I'm going to do to make it under basic conditions is for every H plus I have, I'm going to add an OH minus. So I have 4 H pluses, I need to add 4 OH minuses, but I'm going to do this to both sides of the equation. That way I haven't actually changed the mass balance of the equation. Next what I'm going to do is for every H plus and OH minus I have on the same side of the equation, those are going to combine to form waters. And then I'll rewrite the equation. So when I rewrite the equation, I end up with those 4 waters present instead of 4H plus 4H minus. Notice though, remember I tacked on the 4OH minus to the product side. I had to do that. So whichever side I have H pluses, I add that same number of OH minuses to both sides of the equation. Then whichever side I had the H plus on, those become waters when combined with those OH minuses. Now what I can do is I can simplify that equation. I have 4 waters on the reactant side, 2 waters on the product side. Well, if I start with 4 waters and end with 2 waters, really the only thing that's part of the equation is 2 waters. So I can simplify things. So balanced under basic conditions, this equation would look like this. So those are the steps involved in balancing redox reactions. You need to take note of those steps and follow them. And this is going to come with practice. So you need to practice examples of these. Okay. The next thing we're going to talk about is we're going to talk about the different types of redox reactions we may run across. Okay, so when looking at types, this is going to help us predict products that could be formed. So these types, we have a combination reaction. If I combine potassium solid and chlorine gas, I'm going to make some sort of compound between those two. Well, when I make that compound, this is going to be a redox reaction because both of those have a 0 oxidation number at the moment. Redox reaction means something's going to be reduced, something's going to be oxidized. Well, potassium gives up an electron to the chlorine, and we end up with KCl, solid. Now this isn't balanced. I'm not balancing these. All I'm doing is predicting the products. But that's a combination reaction. I take two elements, combine it to form a compound. That's a redox reaction. We can look at decomposition. Start with a compound, and if it breaks up into its elements, I'd get mercury liquid and O2 gas. Okay, that's a redox reaction. That's a decomposition reaction. I could have a combustion reaction, so taking some organic compound, reacting it with O2. In a combustion reaction, my products are going to be CO2 and water. That's a redox reaction. Okay, so combination, decomposition, combustion, those are relatively easy to predict as far as the end products go. The next one's going to be a little bit trickier. It's going to be something called displacement. With displacement, we're going to have one element displace another. So, when that displacement occurs, we could have formation of hydrogen gas. So if I take lithium solid, put it in water, I'll actually produce hydrogen gas and lithium hydroxide. The lithium has displaced the hydrogen from the water. Okay, that's what displacement means. We can also have displacement of metals by each other. So if I put zinc solid in a copper sulfate solution, I'll end up forming copper solid and zinc sulfate. The copper and the zinc have switched places. Now this is going to be a little bit trickier to predict products and to predict whether a reaction will actually occur or not. That's why we need something called the activity series. So as we look at this table, we can see that the strength of the reducing agent goes up. All right. With this table, what that increase in strength as we go up the table means is that any metal can be oxidized by ions of the elements below it. So let's go back to the zinc and copper. Where's zinc at on this table? And where's copper at on this table? Well, zinc is above copper on this table, so when I put zinc solid in a copper 2+ ion solution, the zinc displaces the copper. If I were to take copper solid and put it in a zinc 2+ solution, the copper and zinc wouldn't switch places because the zinc is higher on the table than the copper. So, ions of metals higher up on the table won't displace the solid forms of the metals below it. Ions of metals lower on the table will displace the solid form of the metals above it. That's why zinc can replace copper, but copper can't replace zinc. Right. Also, metals below H2 cannot displace H2, so they'll have no reaction with water or acids. So if we look at that, those metals, copper, mercury, silver, gold, well, silver and gold, those are definitely highly unreactive metals. That's one of the aspects of them that makes them precious metals. So you could put acid on them, nothing's going to happen to them. Okay. The other things that we can look at here in this table, you can see the strength slowly increases as we go up. Basically, some metals can displace hydrogen from an acid. Some of them can displace hydrogen from steam, which is heated water. Some of them can displace hydrogen directly from water. So let's use this table to predict products. Alright, so if I have nickel and HNO3, what would I form? Well, I'd form nickel nitrate and H2 gas. If I look back on that table, nickel can displace hydrogen from an acid. Alright, magnesium with barium nitrate. Well, if I look at that table, barium is higher up than the magnesium, so there's going to be no reaction. What about tin with water? Well, tin isn't going to be strong enough to displace the hydrogen from the water. It would be strong enough to displace it from like an acid, but it's not strong enough to displace it from water, so there'd be no reaction. Okay, so using that activity series, you can predict general idea of whether a reaction will occur or not. You should also be able to predict products based upon those 4 different types of redox reactions we talked about. All right, and just a couple of more examples. I'm not going to work through these problems, but these are types of problems that you'd run across. So you can see this one's a little bit more complicated, got a lot more oxygens in it. And this one under basic conditions, it's a little bit more complicated as well. Okay, those are ones that you could practice. Most of the stuff you're going to want to look in your book, find practice problems, practice them, and get this down. But using those rules I gave you for oxidation numbers, using those rules I gave you for balancing redox reactions, go through those, use those. Those are going to help you get the right answer. All right, and that's it for redox reactions.